We're waiting for the green light from the Zoom. Okay, so good afternoon, everyone. I would like to welcome you to the Spring 2022 Untitled Center for Energy and the Environment Highlight Seminar. It is my pleasure today to introduce our speaker, Dr. Bill Banholzer from the University of Wisconsin. So Bill received a bachelor's degree from Marquette University in chemistry and then master's and PhD degrees from the University of Illinois in chemical engineering. And then he started a very illustrious industrial career. He was first at General Electric, where he rose and became the Vice President of Global Technology at GE Advanced Materials, and he led the worldwide research enterprise at GE. He then moved to Dow Chemicals, where he became the Executive Vice President and Chief Technology Officer. During his leadership, the innovation pipeline at Dow tripled from 10 billion to 30 billion, and for his leadership and efforts, he has received numerous awards. If I were to list them, he wouldn't have time for his presentation. So I'll just say that then also he established, as the CTO at Dow, a research collaboration with universities. So the entire program was a $250 million program for joint research between universities and Dow. After he retired from Dow, he joined University of Wisconsin in a joint appointment between the Chemical Engineering Department, Chemistry, and the Wisconsin Energy Institute. And he continues to be very active. He's a member of many advisory boards, boards of directors. And as I said, he has received numerous awards, including being elected to the National Academy of Engineering in 2002. Bill is thinking a lot about energy and energy transitions, and as always, I'm sure he will be giving a very thought-provoking talk. So please join me in welcoming Bill. And then maybe a quick note for the Zoom participants. Please send your questions to the Q&A chat so then we can read them to Bill. So,
thank you.
Thanks.
Well, thank you, and it's great seeing Christos again. I think you guys are really lucky to have him here. His kind of work is critical. Technical economic analysis, I think, is fundamental to how we look at energy and problems in general. So I think we all know, especially here, that energy is critical. It is important to our standard of living. It often defines our standard of living. It doesn't just heat our homes and drive our cars, but there's no materials without energy, and there's no medical standard of care, there's no water. You know, we don't have fertilizer if we don't have natural gas, and if we don't have fertilizer, we can't feed the world, so it's not an understatement to say energy is life. You're probably asking, well, what's the chemical engineer, a guy from Dow, talking about energy? Well, what you call feedstocks or fuels, we call feedstocks. So the petrochemical industry is intimately tied to the fuels industry. And so a lot of my interest in energy came from looking at alternative feedstocks and sustainable material and understanding what happened when 2007 energy spiked to $150 a barrel and natural gas was $14 a million BTU. It was a big motivation to try to find new technologies. Coupled on top of that, sustainability. So I think it's really not only important, but I also believe engineering is just essential. I always loved being an engineer because we take all the science and showing what's possible, but we put another lens on it to say what's really practical and what are the costs of some of this. And that's where I think engineering has a unique place in society. I also would be candid to tell you I think we're letting society down. I think we have gotten so enamored with silver bullets and the hype that we're not doing an adequate job of actually giving a presentation on what's practical, not what's possible. So our scientific techniques can deliver all kinds of new technology, but what's really going to be practical? And so today I'm going to try to give you some of my personal examples of things that I've run across of where I think simple engineering would give you answers, and sometimes we don't do it. And then I want to talk a little bit more about hydrogen and biofuels, and at the end, just general sustainability and what does that really mean. But the first thing we've got to always recognize, I got to share my screen here. energy is a commercial enterprise. The government doesn't give us energy, utilities give us energy, and they have to compete in capital markets with everybody else to get the capital to build the plants to give us our energy or build the refineries. So they have to have a return on investment. Now it's highly regulated, so it's very complicated, as you all know, because we've got all these regulations, but it's still a commercial enterprise. And so that idea of what's practical and what can we afford is essential if we're going to look at what's really going to happen and help us transition. And then when I look at business, there's three simple questions. First, you got to say, well, what do people want? It doesn't matter if you're a new pharmaceutical or if you're a materials company or Starbucks. You better have a product that people really want. So you better have a yes to that. The second one, though, is, but what will people pay for? And that is a very important question. Most people get it wrong because I could want a lot of stuff. I may want a calculator for my iPhone, but that doesn't mean I'm going to pay 99 cents for a calculator. I should get a calculator for free. So understanding what people will pay for is critical. And in energy, it's especially important. So we have a broad global awareness of climate change and doing something different. But you can't confuse an awareness of a problem with a willingness to do something about it. When you pay for something, you have to make trade-offs. And in energy, for decades now, we've been able to buy green energy. When you go to your utility bill, you can say, I want, green energy. And usually there's a premium associated with that. 0.84% of the United States signs up for green energy. Not 8.4, 0.84. 99% of the population today won't pay for more sustainable energy. So they may want it. Oh, now switch. Sorry about that. So hopefully you can hear me now. I apologize for those on Zoom. But to reiterate what I was saying is that today, 99% of the U.S. population will not pay for energy or sustainable energy. In fact, they don't like paying what they're currently paying for gas and and automotive gasoline. But the third question is, what can people afford? This is more a global, when you start thinking about the United States, my contention, which may be debatable and I could be wrong, is if we want to go to a decarbonized energy grid or fuels, it's going to cost us more money. And the reason for that is we spent decades, almost a century, trying to reduce cost, trying to make materials cheaper, make energy cheaper. And so if we're going to do something different, if there was a lower cost alternative, we would have been doing that. So I think a big miss in the opportunity when you talk about energy is to be candid about what things are really going to cost. And you need to be successful in business, yes, yes, and yes, or you don't succeed. So we have had a change in our energy sources. It's been a natural evolution. We started with burning wood, and we made, the first Model T Ford was run on ethanol from corn. So it's not that this is new technology, but we moved away from it. And then this shows, I'm sure you've seen class about, but the transition has been a march to higher and higher energy density fuels. And why we did that is that it lowers capital costs, what it costs to build the plant, and it lowers variable cost. Higher energy materials, it's a lot easier to start with a very pure hydrocarbon feedstock than it is a biomass or carbohydrate feedstock. And so if we're going to change from that, you've got to ask, well, why? Just because we think CO2 is a problem, will we pay for it? And some will argue, well, Bill, you're not accounting for the CO2 externalities and the cost of floods and everything else. But our society doesn't value that right now. We don't have carbon taxes. And could we? Sure. But I'm confining my comments to the current structure that we have right now. And given that structure and given what I said earlier about energy has to have a return on investment, if you are a utility company and you're going to have a lower cost, you are going to benefit your clients. If you're going to add cost, you're going to have to get somebody to approve that, and you're going to have to get them to go around with it. And as I said, 99% of people don't want to pay for more. Now this is really profound. It's not trivial. This is a graph that shows you the capital intensity. So how much does it cost to build a plant? And if you use fossil fuels, it costs about $10 of capital for 1 million BTU. If you look at ethanol or biorefineries, one, the scale is very small, but second, your capital costs are 3 to 10 times higher. And that capital is not free. Somebody's got to have a return on investment. I can build 3 refineries for the cost of at least the same output in ethanol plants. So we have to understand the context of cost, and that's why the work that Christos and other people do is essential to help us frame what are these trade-offs going to be. And it could be that we as a group want to accept that this is an issue and will pay more, but then the issue is there's only so much GDP in the United States and in the world, and we don't have enough health care that we can afford, or our infrastructure is crumbling, or education. We have a lot of demands on that GDP, and we're already living beyond our GDP based on our deficits. So this capital efficiency is something that you've got to really try to get your hands around, especially when you look at variability and what I can actually get these days in terms of materials and plants. Now, I've long had the supposition that society just doesn't understand energy, and I think this is a great PNAS paper that actually gives us some data around that. And it's somewhat obvious. You know, we know what a gallon of milk looks like, and we know what a pound of hamburger looks like, but you don't have the same innate feel for a kilowatt hour or a million BTU. And then we price things differently. We price oil in dollars per barrel, but we price gas in dollars per gallon. And then we look at a gallon of gas, and people don't understand a gallon of ethanol has a third less energy than a gallon of gasoline. So that dollar per gallon price is really not the right metric if you're trying about how many miles per gallon am I going to get. So we've got this complicated system, and the reality is it doesn't take any more effort for you to flip on a switch and turn on your air conditioner than it does to turn on the lights. So what this graph shows is the actual energy that different things use versus their perception of energy, which is on the y-axis, and the actual energy. And if we had a good understanding of energy, and you asked, this is a paper that asked, you know, the general population, what do you think? If we were good, we'd be on a 45 degree. Our actual and perception would line up. But you can see there's hardly, this line's flat. People think that, you know, a clothes dryer or a washing machine aren't a whole lot different than a dishwasher or a light bulb. And in fact, in the next slide, this is how bad it is. If you ask in light bulb units, all right, you know what a light bulb is. We have this innate feel, and even there we're confused because light is in lumens, not watts. If you say, it's dark in my room, I'm going to put my 60-watt bulb and replace it with 100 watts, you're not necessarily getting any more efficient. You're just getting more light out of it. And so lumens per watt is the figure of merit for a light bulb, but nobody knows what a lumen is. You know, we struggle with kilowatt hours, but that at least we see in a bill. Well, if you say, how many light bulbs does an air conditioner for a typical 1,500 square foot house use? And the number is 2. And the real number is like 70. I mean, people are off an order of magnitude in understanding energy. So it's no doubt that we've got an educational issue to go by. And I had also in my GE career ran R&D for GE Lighting, so historical business. And we struggled with trying to explain energy efficiency. So if you talk to any business, they'll tell you 80% of the cost of light is the electricity that you use. So when I put in my 60-watt bulb and I put in a 34-watt compact fluorescent, or 15-watt, watts is what you pay for, but they give you the same amount of light. And compact fluorescence has been a huge issue of people look at the sticker shock. So another issue with consumers is that we don't like to pay for things up front. And so a light bulb that's 60 cents, a light bulb that's $3.40, you know, now they might be $2.40, but it's still, people don't want to pay $5. They think, I can buy 5 of these for the other ones. But when you look at the energy that's used, because the compact fluorescent over its life is so much more efficient, and the fact compact fluorescent lights last longer than incandescent. That upfront price has to be amortized over the life. There was actually a Philips commercial that showed a student showing up in his dorm and screwing in a compact fluorescent light, and then fast forward and he's got his mortarboard on, he's graduating, unscrewing his light bulb to take it with him because they last longer. But you got to think about that, and to consumers as a problem, just don't. So we've got an educational issue and a misperception issue. This leads to a whole bunch of confusion. On top of that, we have set expectations because we've been so successful in miniaturization of electronic components. And if you look at Moore's Law, it's very familiar. Well, this is a restatement of Moore's Law. It's Kumi's Law, where you look at the cost per calculation. And it's gone up over time 7 orders of magnitude. You know, there's hardly anything I can think of that we have improved 7 orders of magnitude. It's actually 8 now. So now we do have maturity curves. And so if you look at things like ethylene compression or air conditioning efficiency or reverse osmosis efficiency, we have gotten better, but you can see there's no 7 orders of magnitude. I mean, look at the difference here between what we've done, because this is based on miniaturization. When you talk about bulk things like moving people through air and the friction that the tires in the air, the drag that the car creates, or an airplane, or heating your house, you don't have those same operation mechanisms. So when you hear things like Moore's law for solar or Moore's law for wind, they're misplaced. It's not these orders of magnitude changes. And certainly there's improvement, but you can see, you know, it's sort of one. You get an order of magnitude improvement, something from initial to launch, maybe 2. That's really pretty good. Now, there also is a experience curve, which the more I build something, the better I get at it. And it has to do a lot with scale. So if you look at installed capacity or how much we've actually built, I get better. So you can see where costs have come down. You know, ethanol was pretty high, but as we got it more efficient, nuclear, hydroelectric really hasn't changed much, because hydroelectric suffers from the fundamental physics of there's only so much pressure drop. You can make your dam only so high, and that's the amount of pressure drop you've got to deal with. So it's harder to get more efficiency out of it. But an engineer, NGCC, natural gas combined cycle, has gotten very good. Today, large steam gas turbines can have 60% thermal efficiency. That is really pretty good. But it's not going from 0.6 to 60. It was, sort of single digits to 60%. It's this 1 or 2 orders of magnitude, not these 7 or 8 orders of magnitude. So when people look at how good our cell phones have gotten and how fast our computers are and how cheap they are, and you extend that to the energy infrastructure or materials, it's an inaccurate comparison. And there also is the idea of scale, and that's another thing that seems to be lost in a lot of our energy discussion, is the scale of energy is just enormous. And if we look at, as scale gets bigger, we tend to get more efficient, but it flattens out. Again, you can see these curves, they swing over. They don't just keep going up. And when you have any of these macroscopic trends, it has a real issue. Now, we all want sustainability, and that's another problem of sustainability has gotten to be very confusing. If I asked you what's your definition of sustainability, we'd probably get a lot of diversity in it. But we have a general feeling of it should be better. It should be, but it's sustainability greenhouse gases, or is it landfill, or is it water pollution, and so it's all of the above. I mean, we want everything. And so today, you look at, this is just a Google search of how often do you hear sustainability in the literature that's out there. If you look at this, by 2026, sustainability is going to be about once a page. So only in a few more years, we're going to see this everywhere. And then in 2052, it's going to be on the average of once per sentence. And then up here, whatever, 2050, sustainability will be the only thing that'll be on there. I mean, we talk about it all the time, but we really don't have an understanding. In fact, I was giving a talk, and this was back when I was still working for Dow, and I was talking about polymers and trying to make garbage bags thinner so that you use less material, and it's a big part of can we use less is a big opportunity. And one of those persons from the audience says, well, but why don't you just make everything biodegradable? And now this was a talk that was sort of related to climate change and what you could do. And I said, well, this is an issue. If you want to make things biodegradable, and you can do that. You can put in those linkages. It's not a big deal. But first of all, you got to make sure you engineer it well so the product doesn't start leaking on the shelf because it starts degrading in Texas when it's hot, or in the truck. But if you stick it in a landfill and you take plastic, which we're pretty efficient at taking hydrocarbons and making plastic out of them. We don't lose much of the carbon. And then I bury it, that carbon's sequestered. But if you make it biodegradable, that carbon goes right up into the atmosphere again. I haven't done anything with greenhouse gas loads, but I have lowered my landfill. So you've got sometimes these orthogonal vectors of what sustainability really means. And trying to understand all that is a complicated problem. But the combination of, I'd say, societies need to be better educated on energy, which is our collective responsibility, and then a concern to really want to do something about sustainability, and then a very short attention span, and then a struggle with things like depreciated cash flow or the electric light payback. And you put all those together and you're ripe for hype. And so in some cases, you don't need to do much work to figure out. Now, this is an example, and I just chose this one because it actually, one of the CEOs or co-founders was from Princeton. So it's got 2 guys from Princeton and New Jersey. So I thought, well, it's appropriate here. And what they said is just two graduate students, one from Princeton and Northwestern, have come up with a way to take CO2, which we want to get rid of, and make a plastic out of it. And they call it AirFlex. And at the last paragraph, so this is, they said, you know, we're very pleased that we received our 7th patent and about this technology. So think of this. I can take CO2, which we want to sequester. I can turn it into plastic. They have 7 patents on it. Boy, that's a company I want to invest in, right? If you stop there. So I got curious, and I went and looked up their patents. And in 6 of their patents, this is the first figure I see. For ruminant recirculation, so they're going to capture the methane on cars, on cows. This is, you know, you could argue, well, we got point sources here and we got to capture it. But I mean, that's the basis of your patent, is pretty nonsense. And by the way, those polymers have been known for decades. Biopolymers generally are crappier. They cost more, and we went away from them because they just don't work as well. The polylactic acid is an old polymer, but if you remember how fickle consumers are, Sunchip, the Sunchip bags, Pepsi said, I'm going to make a sustainable packaging early on. I want to do good. We're going to replace our packaging with polylactic acid, and we make our Sunchip bags out of it. Now, if you do that, it's a little harder to process. It certainly said, we'll pay a little more for the bag, but we're going to feel good, and people will buy it because we're trying to do good. And if I said to you, what are the CTQs, critical to quality things for a package? Well, it's got to hold the chips. It can't fall apart. You got to be able to print on it so it looks nice and people will buy your chips. And it's got to have the right barrier properties so they don't go stale. And you can do all of that with a foil-lined polylactic acid. You'll pay more for it, but you could do that. But if you YouTube polylactic acid or Sunchip bag and noise, when you open it, it makes this horrendous crackling noise. And they had to take it off the market because us all as consumers said, we don't want a bag that makes that much noise. That's the trade-off we made. You could be a little more sustainable. They'd pay more for it. You didn't like the noise that it generated. So these are some of the hurdles that were up. And then we have things like this out there that, you know, somebody probably put money into it. The next one is actually, I couldn't make this up. It really happened. I was a CTO of Dow, and so a guy came up to me and said, look, you know, this is back right when we realized carbon capture and sequestration is very important. And I had this guy, CEO of a company called Skynex, come up and say, we would like your help. And so here's what their value proposition was, is that they're committed to reducing greenhouse gases, and coal plants generate a ton of CO2, and they want to actually get the CO2 out of the stack using sodium hydroxide. So you got a very strong base, weak acid. You can do that. It works. It's possible. It's not even that sophisticated chemistry, right? And this is the idea. We're going to take coal and we're going to clean it up. But they didn't know how to make sodium hydroxide, so they wanted Dow's help, who at the time was the biggest U.S. manufacturer of sodium hydroxide and chlorine. So here's a video on one of their pieces, one of these local news sources that I think is entertaining.
In this country, there are rules limiting pollution released by power plants, but there are no rules limiting the kind of pollution responsible for climate change. Most experts, though, say that kind of regulation is coming. In fact, there's now a green rush to create technologies that reduce global warming pollution. As David Schechter reports for Project Green, one solution made in Texas is good enough to eat.
The future of energy is going to require some amount of coal power to bridge us through to the future.
Big Brown, south of Dallas, powers nearly 600,000 homes in North Texas and has a voracious appetite for coal. But coal is inherently dirty. Luminant, formerly a part of TXU, is required by law to remove mercury and other pollutants from its coal plant exhaust.
The CO2 is the most elusive.
But not carbon dioxide.
It's very hard to capture.
Which most scientists agree is the cause of global warming.
Carbon dioxide is the culprit.
This pile represents less than a day's worth of coal that's burnt at Big Brown. And lately they've been asking an interesting question about that pile. What if you could take all the CO2 that's in it and turn it into something clean enough to eat?
And I really think it's probably the most important problem that we've got to solve as a species going forward.
Inside this trailer at Big Brown, an Austin company called Skyonic.
We'll open the valve. The analyzer will take a sample of the flue gas.
From the flue gas, run through our process.
So it pumps at a faster rate.
is racing to make history and maybe change it. Joe Jones is CEO.
Well, if I were to ask you who the second person to fly the Atlantic is,
No idea.
who's the first?
Lindbergh.
Everybody knows that, 85 years later?
They're one of many companies searching for the best way to strip carbon dioxide from power plant exhaust.
Yeah, it seemed obvious to me that it could just be done and done easily.
Skyonic taps a little exhaust off the plant and basically mixes it with salt and water. When the exhaust goes back, they say the carbon dioxide is gone.
All the bad stuff's taken out, and only good stuff remains.
The process creates some interesting byproducts. Hydrogen, which is a clean fuel, chlorine, an industrial chemical,
Saves energy for the whole nation.
and baking soda,
CO2 winds up as solid bicarbonate of soda.
where all the carbon dioxide is locked up.
We've got some cookies that are made with that baking soda, and I will tell you that the baking soda in this is more pure than what you brushed your teeth with this morning, so let's give it a bite. Taste of success. It's good.
It doesn't taste like pollution at all.
But what may impress the energy industry even more is the process actually makes money. Skyonic says selling the hydrogen and chlorine will raise more money than it costs to build the whole system.
In order to do social good, I found that the only things that get done are those that get funded. And the only things that get funded are those that make profits.
As for the baking soda, well, it turns out the world already has plenty of it. So Skyonic's plans call for burying the baking soda and the carbon dioxide back in the hole where the coal came from. Though it might be fun to just save a little.
Greenhouse gases taste good as gingerbread, but they also taste good as in chocolate cookies. I think better.
It's good. I think these are better too.
Yeah,
David Schechter, Channel 8 News.
good stuff.
In this country, there are rules.
So that's what the public sees. And Jones actually is a chemical engineer, I'm sorry to admit. Not from here, and he shows up and he asks us, and this took about 10 seconds to say, did you ever close the energy balance on this? Because if you remember what he said, we take salt and CO2 when we make sodium bicarbonate. He left out a little thing, which is, you don't take salt. You take sodium hydroxide. You take salt water, and you put a ton of electricity in there to make chlorine and sodium hydroxide. He just left that out, and he said, this is going to make money. Well, here's just a few simple things. So the chemistry is pretty simple. We've been doing this at a large scale for decades, 100 years. But if you look at how much sodium hydroxide you need to take and produce for a 600 megawatt coal power plant, you need 7 billion pounds. So you've taken a $1 billion coal plant and added a $3 billion chloralkali acid next to it. That's going to be a little bit expensive. But the bigger issue is, if you look at the electricity you need a gigawatt of power to make that amount of sodium hydroxide. You have a 600 megawatt plant, you got to go and take every electron you make and go buy 400 megawatts more power to make enough sodium hydroxide to capture the CO2. I mean, that's about my first reaction. I fell on the floor. I mean, you can't, he's a chemical engineer and he says this. And by the way, the amount of chlorine you make, the world didn't need that. And you're going to bury this. And we all know what happens when we made our volcanoes as freshmen or early high school students. We put sodium bicarbonate and vinegar in it. You get any acid rain, you better make sure you've got that put somewhere where it's not going to see any acidic environment. The CO2 is just going to go. I mean, so this is, oh, well, Bill, I mean, I agree, it's pretty absurd. Well, here's the sad thing is, DOE gave them $28 million. They got $128 million to build a plant. They shouldn't have gotten a pilot plant built. Yet our esteemed colleagues at the Department of Energy funded this. And I actually ran into the Undersecretary for Fossil Fuels when I was in DOE one day, and I said, have you heard about this? He said, well, we just want to know what our options are. This is never going to be an option. Why would you put $1? This is my money that's going to this nonsense. But this is the problem when you've got this strong desire to do something, and it looks pretty good. Geez, we can make cookies out of our CO2 and clean up the world. So it's a problem. Now, I am old enough to remember the first Super Bowl. And at the first Super Bowl, they had so I'm transitioning to biofuels, to display why did they fail. And I was very outspoken very early on saying this is not going to work. And I want to just give you a very high level, again, saying we should never have gotten as far into biofuels as we did if we had done simple energy and mass balances and a little technical economic analysis. So, but at this first Super Bowl, they had two guys at each opposing end zones with jetpacks, and they flew up and they met at the 50-yard line and they shook hands because the AFL and NFL were coming together to play this game. It was inspirational. And I loved it because I'm going to have a jetpack someday. We're going to be flying around with jetpacks. But it's the same thing but look, there's limitations. We can only carry so much weight. The only reason they flew 100 yards is because that's about, you can fly a few hundred yards, but that's all a jetpack can do. But it was, at the time, there was pictures of we were not going to have to need cars. We were going to fly around in jetpacks. Well, here's the fundamental of energy and chemistry. The world is built on oxidation. We start out with things that are very reduced, methane or oil or natural gas. So up here on the left, and then the y-axis is the heat of combustion. And then we burn them. We combust them with oxygen. Even you and I do that. We bring in carbohydrates and food, and then we oxidatively decompose those, and we expire. The whole world goes down because that's the way we generate energy. So anytime somebody talks about going up, so we're going to take biomass, carbohydrates, and we're going to go up to oil or fuels or biomaterials, you got to ask, what's the reducing agent? Where does that come from? And how much CO2 does that generate? And we just ignored all that. But then there's even a more simplistic way to look at this. So I had to deal with not always technically interested board of directors, and we had a big program looking at coal. Could you make plastics out of coal? Because China has an abundance of coal, and we had a big program to look at coal to olefins. But when I'm taking ethane and I'm making ethylene, they look pretty close. They're pretty close in energy. That's why I don't waste much carbon. My carbon efficiencies are very high. And then when I make ethylene into polyethylene, I lose next to nothing. But if I'm going to try to take coal, I'm going to have to reduce it, which means I'm going to have to generate a ton of CO2, because the way I'm going to reduce some of this carbon and get rid of all those red balls there, the oxygens, I've got to eject CO2. So that's how coal to olefins work. Even carbohydrates, if you look at fermentation, we've got to remember that we put 6 carbons in, we get 4 carbons out as CO2, and 2 carbons come out as ethanol. But it's not that we're going up in energy. We're taking and reapportioning our energy so that 4 carbons go down to CO2 and 2 go up. But anytime you look at molecules, these space-filling models, and say, the further away my feedstock looks from my product, the more capital I'm going to have, the lower my carbon efficiency is going to have. So simplistically, this doesn't look like this looks like this is going to be more expensive than that. That's a level of engineering you need to do to come up with what are pretty simplistic guiding principles. So we're built on oxidation. Well, this is a curve of dollars of various chemicals versus our usage. And so the y-axis is the dollars per ton, not dollars per milligram. So the other thing is, when you think about pharmaceuticals or insecticides or herbicides, those are dollars per gram or even dollars per milligram. Most large-scale things we use are priced in dollars per ton, and then we use a lot of tons, millions of tons. So this is what the chemical world looks like, and it's not a straight line. These are the specialties way up here, and then these are semi-commodities, and these are really commodities. But if you take all of that chemicals and look at where fuels are way out here. One, they're almost on the x-axis because we don't care about fuels. We just want the fuel value. We don't care about their structure. We're not asking them to do anything but burn. And so fuels sell for fuel value. So when we look at biofuels, we're going to take an expensive feedstock and go after the biggest volume, commoditized part of our energy cycle. And so it had a price problem. It had a utility problem, a carbon efficiency problem. And it's no wonder. Now, the sad thing is we spent, in the last time I looked, over $3 billion collectively from private and public companies trying to make biofuels work. And this is a graph from DOE's data of the old days of, where did they see, this is the 2 components of cost. One is the capital cost. What does it cost me to build a plant? So if you remember that slide that said fossil fuel plants have better capital efficiency than biofuel plants. And then your variable cost. What does it cost me to get in corn or get in oil or natural gas, which is on the y-axis. And so this is where petroleum ends up. And so going down in that direction towards ordinate is lower cost. If I go up this way, and depending on what you think your cost of capital is, your interest rate is, that's the slope of those lines. So you can trade off a higher capital plant for a lower variable cost. So I could build a plant from coal because coal is very cheap and be up here. Well, that's not as efficient as if I'm coming from fossil fuels, but you can make those trade-offs. Well, this is what people thought for biofuels. Yeah, we're way up here, but here's where we're going to be by 2017. And they had all these projections of how it was going to go down that I could never figure out where these came from. And the reality has been exactly the opposite. Fossil fuels haven't gone up anywhere near as much as they thought they were going to, and biofuels never came down. In fact, they've gone the other way, and almost everybody's bankrupt. I don't think there's any commercial cellulosic ethanol plants working anywhere anymore because it just doesn't work. It's too expensive. And the other thing we've got to recognize that there is a significant lack of understanding of the realities of how the world works in capital allocation. So DOE publishes a lot of feasibility studies based on nth plant economics. So remember when we were talking about scaling, the more you build, the cheaper things get? Well, they'll say, could this technology work? Could you make cellulosic ethanol work? And you assume some kind of maturity curve, and a 50th plant or 100th plant they call the nth plant. And they say, well, yeah, see, that cost is starting to get to be at parity. Now, I spent 30 years in industry. If your first plant isn't cost competitive, you don't get money for the second plant. You never get to that nth plant economics unless there's some perturbation of subsidies or some other force to do it. So now this is the way the world looks today. I mean, this could change dramatically if we put a carbon tax on things, because these things don't all have the same carbon load in the atmosphere, but we don't. And so people will say, yeah, but Europe does, but we need to do this at a global scale. And if you don't, you just move industries from one continent or one place to the other. We can't even agree on exchange rates. How are we ever going to agree on a global carbon tax? So it could happen. I'm not saying it's impossible, but I'm just trying to say, is it possible? And if I had to allocate and go ask for a loan that I was going to pay you back for, what assumptions do I make when I do that? So my argument would be that biofuels was ill-conceived to start with, and we should never put, billions and billions of dollars went into it. And again, Kiora, all these companies went bankrupt. Another thing about energy is this scale thing. Scale really matters. And so a little plant, somebody talks about, well, I made a plant that's got 100 kilowatt hours. That's a nit. I could get a generator that big for my home. You've got to be talking about terawatts and at least gigawatts for demonstration plants. This is just showing you the yearly flux of how big a refinery is versus where ethanol plants are. There's no efficiency at scale here. In chemical engineering, we've learned scale matters. The 6/10 scaling rule, for the most part, is pretty accurate. And scale, when you're moving big things, back to this possible, if I was a miner, I've got to move volumes of material, tons of material, I could hire drivers and get 150 F-150s and drive that around at a half ton at a time. Well, we don't do that in mine. We use these big trucks because it's cheaper. That truck costs way more, but it's only got one driver. We move a ton at once. When you're doing big scale things, scale matters, and scale is directly related to cost. Now, the other thing that I really find absent in a lot of the bio literature is we have so many people that are so ecstatic about increasing the titer from hundreds of parts per million to maybe a few percent. A few percent is still a very dilute feedstock, and you should remember that most chemical plants and refineries, half of the capital cost and usually half the energy is in the separation and purifications. Biological processes are even worse. Now, if I am trying, and I'm not against biotechnology, I doubled the Dow AgriScience biochemistry budget from $300 million to $600 million, because in agriculture, it's fundamental to changing how we do agriculture. But it's applied to something that sells for dollars per milligram, not something that sells for dollars per ton. So you've got to remember, separation costs are huge. An ethanol refinery makes wine. It doesn't make grain alcohol. There's a lot of costs that go with that. And corn is not decoupled from the price of natural gas because we need fertilizer, and fertilizer comes from ammonia. So very interrelated systems and very complicated. The last thing I want to try to touch on briefly is hydrogen, because it's so much in the news now. And I will show my age here. I think this is about my 4th hydrogen hype cycle. And I think it is a hype cycle. And I'm going to explain my position. And again, I could be wrong, and I look forward to you guys telling me what I'm missing here. But Stephen Chu was the first time we had a Secretary of Energy who was a Nobel laureate technology. I was so optimistic because he now is not just a governor or something. I mean, he has a technical background and could analyze this stuff. And in 2009, he said, you can read the quote, but it takes 4 miracles for a hydrogen economy. We don't know how to make it without emissions. We don't know how to store it. We don't know how to make fuel cells cheap. And he said, the last time I looked, it only takes 2 miracles to be a saint. So this is a pretty long technical putt. But today he said, or just recently, 2019, said, hey, get ready for 1.5 cents a kilowatt hour electricity. It could unleash the hydrogen economy. So if you're a standard consumer and you have a Nobel laureate saying these kind of things, and well, how do you sort this out? Airbus says they're going to have hydrogen-powered planes, and so it is very contemporary, and it could be a savior. But we've got to remember, hydrogen, there is not a primary source of hydrogen except the sun. We don't have hydrogen mines. Hydrogen has to have a primary energy source, and therein lies the problem. So if you look at today, 99% of hydrogen is made by ammonia, or by taking methane and using steam hydrogen reforming to make that hydrogen. Or it's using autothermal reformers or partial oxidation. But it comes from natural gas, and all ammonia that needs that hydrogen comes from natural gas. And it's a real issue right now if you've been following the news. You know, current prices in Europe for natural gas are $70 to $100 a million BTU. Their fertilizer plants are shutting down because you can't make fertilizer at $100 a million BTU. Just for comparison, we're complaining because we went from $2.50 to $4.50. So the United States is very lucky that we can afford to still run fertilizer plants, and our natural gas bills are up, but they're not up anywhere near like they are in Europe. But if you look at, I want to now do electrolysis. So again, it's possible. I can take water, put in electricity, and get hydrogen out with no emissions, if that electricity has got no emissions, but it's 5 times the energy content. So that's a big energy penalty. But you know, you got to ask questions. Well, what's the cost of this going to be, and how much capacity do I have? Is the electricity greenhouse free? Am I going to have the ability to store and distribute it? Hydrogen is very explosive. If you want to build an industrial lab and use high-pressure hydrogen into it, you have to have explosion-proof motors. You have to have a blowout wall. It's very dangerous. You know, we have to take our shoes off because they're worried what we might have in our shoes when we walk through TSA. You have people driving around with high-pressure hydrogen. That has tremendous potential for disruption. Could we manage it successfully? Yeah, we managed hydrogen successfully at an industrial scale. Could you do that distributedly? Sure, but it's very expensive, and you're going to have a ton of, you're going to include our risk portfolio significantly. But my big issue is the assumptions and the rhetoric around this is just too hyped. So this is an NREL's estimate of what is it going to take to get hydrogen to be $1 to $2 a kilogram. So that's going to be a reasonable fuel price. And the biggest assumption is that they're going to have electricity at 1.5 to 2 cents a kilowatt hour. It's amazing. If you look at, if I could take the electrolyzer capital cost and cut that in half, that's less important than if I can get just a 5% decrease in my electricity cost, because electricity is so important. Remember that 5x difference. So all this is based on, we're going to have all this free electricity, and it's all going to be renewable, so it's going to be hydrogen free. The hydrogen is going to be carbon free. So that's what's out there, and that's what people are advocating. And I think you just got to do some sanity checks. This just shows that sensitivity of, you know, it doesn't matter what your capital cost is. It's all about electrical costs. So we ought to dig into that. What have electrical costs been? Now, electrical costs, I'll remind you, are a commercial enterprise. They've been trying to get electrical costs down because they can make more profit or they can lower your rates for decades. And this is the industrial rate. This is what you and I pay. This is if you are an industrial user, you have been paying around 6 or 7 cents a kilowatt hour. Nowhere near the 1.5 cents that they say that they're going to have. I mean, back in the 70s, there was cheap oil and some perturbations, but if we could have made 1.5 or 2 cents a kilowatt hour, we would have been doing it long before now. I mean, it's just not hasn't been in the cards. Could it happen? I just don't see a path. But here's how we fall into this: is people show the curve, and this is just one of how solar has come down. And you'll hear, I'm sure you've read headlines, solar's cheaper now than natural gas or fossil fuels. Right? That's something we've all heard, which is true, and it's a half-truth. It's not really true. If you really look at, I actually went to a guy who should know, which is, so there's we look at the utilities. Their job is to stay in business and understand this. And so this is a quote from a webpage from Power South, who said, look, people want me to put in solar. And it's true, I can get solar for $22 a megawatt hour. That looks cheaper than combined cycle natural gas at 29. So that statement, it's cheaper than fossil fuels, is true. But he said, but that's not an apples-to-apples comparison. That's during the day when you've got generation production. I can't rely on this at night, so I'm going to have to put in some kind of storage, and that, you can pick your own number, but let's just say $90 a megawatt hour. And by the way, then I have to put in twice the amount of solar capacity that I need, because I got to charge those batteries. So I've got to put in dollars per megawatt hour plus my storage. There's no way that solar is cheaper than combined cycle for base load. So could it be opportunistically cheaper? Yeah, but could it replace our grid to the extent that people say? it just has got a fundamental issue with storage. And so when you say in 2035 we're going to have 30, 40, 50% renewables, this is a big problem. And this is a guy who ought to know. It's not my numbers. And maybe he's got something wrong, but here's somebody I would listen to. And again, we look at these half-truths of module prices have come down a ton, but the balance of systems, you need inverters, you need transmission lines, those are scale things, and those have not come down. Copper is still expensive, and so if you look at just this curve, that's different than sort of the total cost and levelized way to look at energy and add all these costs in. It's a hard problem to solve, but the bigger issue is this scale thing that I keep repeating myself on is, today solar is 1.3% of our grid electric generation in the United States. This is, EAI's numbers. And wind is 3%. And so if you look at, we want to try to electrify our transportation grid. So we've got to add generation capacity. So this number is only going to go up. And if we want to replace a third of our energy that's currently transportation fuels by electric power, then we need basically double our electric generation capacity. So it's maybe 0.6%, and we want that to be 30 or 40%. That is a massive ramp up that we have never seen. And is it possible? It could be, but then we all got to be candid about how many hundreds of billions of dollars are you willing to spend for that transition, and how are you going to deal with the storage? But the bigger issue is I just don't think it's possible. So I lived through the solar of polycrystalline solar bloom. And then here's another point, because I've seen this and it just boggles my mind. You have CTOs of chemical companies trying to do good and saying, I can electrify my chemistry, which we can do. We can do a lot of electrocatalytic reactions and replace our classical, traditional thermodynamic, chemically driven reactions by replacing thermal chemical energy with electrical energy. And this is what BASF thinks they could use by 2050. And they need 700 terawatts of electricity to convert the chemical electrical processes. This is Germany. Germany's today, the entire industry, not just the chemical industry, only has 270 terawatt hours, and all of Germany is 490. So the chemical manufacturing sector alone needs twice what Germany's making today, and they can't keep their own grid running because they've had a horrendous energy policy. If you read, we can talk about that for another time. So the scale and the amount that's required is just phenomenal. And this all, by the way, has to be renewable, because you're not doing any good if you don't have carbon-free electrical generation. But I was on the board of directors for Dow Corning, who own the biggest world manufacturer of polycrystalline silicon. So the way you make a photovoltaic array is you start out with sand, you do a lot of work, put a lot of energy into it, and you make silicon, but you have to make ultra-pure silicon. So you go through the Siemens process, and Hemlock was the world's biggest producer of polycrystalline semiconductor for both wafers and silicon. And in these days, the prices were $100 a kilogram, and the price to manufacture was lower than that. And it started to climb because solar really started to take off, and there was this huge demand. And your economics 101, if you've got increased demand with no increase in supply, you have a competition and prices go up. And it got up to $450 a kilogram. Well, during this time, Hemlock said to us, well, we'll build another plant. We know you guys, and here's the deal. I'll build the plant, but you give me the money to build the plant, and then I'll give you a reservation of that capacity. So you're going to get this amount of capacity, and I will give you historical contract prices. So let's say $100 a kilogram. So they built a $1 billion ultra-pure silicon plant in Tennessee with their customers' money. But at the same time, this is when the U.S. started to put import duties on solar cells from China. And China said, wait a minute, you're going to put duties on me, then I'm going to put duties on polycrystalline silicon, because that was from the United States or Europe, and so it's tit for tat. But they also said, and I can't depend on you guys, so I am going to invest in my own capacity. And they just drove the price down. They added massive amounts of capacity. They used coal electricity. They used cheaper EHS standards. They just drove the price down like crazy. So, all of a sudden it got to be where the price on the spot price for ultra-pure silicon was lower than the contract price. And so Hemlock actually screwed this up. I was gone, so it wasn't my fault, but they screwed this up, and they didn't lower they needed to follow the spot price, and they didn't, and so people said, I'm not going to buy from you. That plant never got turned on. $1 billion ultra-pure plant in the United States never got turned on because of the trade dynamics between the United States and China. And today, if you look at the production of ultra-pure silicon, this is what it looked like in 2004. You can see hemlock at the top. Today, Wacker is number 3, but almost all the world's polycrystallines, ultra-pure stuff, is made in China. So if the idea, we want to have this massive amount of photovoltaic, and polycrystalline silicon is just the start of that supply chain, because then we've got to make it into ingots, grow it into single crystal or polycrystalline ingots, and then we've got to make wafers, and 97% of the wafers, the United States can't make this without China. And so is it a logical energy policy to say we are going to be dependent on China for our energy policy? I mean, it could be, but Germany did the same thing with natural gas in Russia. That hasn't worked out so well for Europeans. And so you've got to ask, is this a prudent energy policy, or what do I need to do to make sure that if I want to put that much solar in, and I can solve the strategy, and I can solve the cost issue, and I can solve the storage issue, I mean, there is still a lot of miracles that happen here. And by the way, this has got to be cheaper. And we have some EHS people who don't want that much solar footprint in the United States. We don't want wind. We have these competing things. So I just don't see where solar is ever going to be as big as people think it is, or as cheap as they think it's going to be. So I'm going to stop there. I was going to talk about lead and stuff, but I think this is a good stopping point, and it's getting certainly close to time, and be happy to take any questions. Again, I could be wrong on a lot of this stuff. This one, I just can't get from A to B. Transition is a transition, and we try to go, turnkey too fast. So let me stop and see if I can answer any questions for you, or tell me what I'm missing. I have a view, it could be wrong. We're still going to have fossil fuels. I just don't know how your standard of living has to go down so far if we don't have fossil fuels, because it's so important to us. It's just feeding people everything, and it's such a big scale that the transition, I think, is still, I don't know if it'll be the majority, but I think it'll be close. I'm hoping we'll have more renewable. We're not going to have more hydro. I mean, there's just not that much more. I would like to see more nuclear. I think that's smart nuclear, not the way we're doing nuclear today. I mean, you can't have the one through burn. You have to worry about reprocessing. But it seems you could put together a policy that says, first, be honest, guys, it's going to cost you a ton of money. So I'm going to tax you more because we're going to have to do this. Or we're going to regulate it, which means you're going to pay more one way or the other. We're going to accelerate our nuclear programs and try to get over the stigma, which I don't know if that's politically acceptable. I think you should get rid of coal. I mean, we have an abundance of natural gas, and we could be self-sufficient on natural gas, and I don't see why we wouldn't try to accelerate getting rid of coal as fast as we can, because we can match, and we could even with better, we can make natural gas, which is way better than coal. I think like in the Northeast up there, you've got to get them off fuel oil and stuff. I mean, they don't want a natural gas pipeline up there, but they also cut out a transmission line. I don't know, right now, the United States has pretty uniform natural gas prices, except up there, because we don't put the distribution. I think you've got to have smart decisions of how you're going to allocate that. And then you're going to have to look at electrification and say, how much can I work in and how much can I afford? And then just another thought is, we haven't talked about lead, and there's a ton of lead that's released when you make copper. You look at all the auxiliary things to electrify, there's a lot of other things between mining and other things you need. And so rather than make one EV that has a big battery pack, you can make 5 plug-in electric vehicles for that same amount of battery, which would take 80% of it. If I drive around, most of the time I have a plug-in hybrid. That's a good compromise. I use electricity almost all the time, except for long trips. So it's bad because the car is going to cost more, because you got an electric drivetrain and an internal combustion drivetrain. But I can get 5 cars out of that for the same amount of burden on the world that we're going to take ore out. So, I mean, it's things that I think the biggest issue is we can't have an energy policy that changes every 4 years. You can't have a pipeline, and I just was baffled. We shut down supply. We shut down pipelines, we revoke leases, we say now to get your permit, you're going to have to put greenhouse gases in it, and EPA is trying to sort through all that. But the net effect of that is we decreased interest in developing our own hydrocarbon and fossil fuel resources. But then we go to Venezuela and say, could you turn up and get friendly with them? I mean, you could be self-sufficient and not have to make any compromises, but you got to accept it's a transition, and I can't just go. So was it admirable to say I'm going to force people to be more renewable? Sure. It just was not practical in a time frame that's reasonable. And I'm baffled by, why are we surprised that oil and natural gas is so high? You shut off supply. Demand is pretty inelastic. We still drove a little bit, even during the pandemic. there's not enough supply, demand isn't changed, prices go up. And now we've got that globally. So when, you know, you hear administrative officials talk about price got, oil is set globally. I mean, this is, I guess they missed that economic 101 supply demand kind of thing. But I mean, it's a view. I think everybody's opinion is equally valid. I think as long as we make informed decisions, like not trying to do carbon capture for sodium hydroxide and some of that stuff, but we can't have on again, off again. We can't have this is it, and I don't know how you do that in a polarized political, because if you were an investor and you put in all that money in the pipeline, you were told you got the permits, and all of a sudden somebody else comes and says, well, now you don't. Or I had permits to explore in the Gulf Coast, and now you said, no, you don't. Who's going to give you money, or how am I going to invest in it? And I think we just got to be candid. I just don't. I think it's not politically expedient. It's not an easy solution. Energy is a hard problem, really hard.
We have a few more questions.
What's your opinion about the Brazilian sugar cane to alcohol program? That seemed to be fairly successful. Do you have, can you scope that?
Sure. Actually, I know a lot about that because when I was at Dow, we actually started a sugarcane to polyethylene plant because you can, you know, Brazil's got a unique climate and they're very well established in sugar, but and you know, the way you make that, you've got to have, you buy a bunch of acreage. It's dependent on how big your plant's going to be. And you plant 1 year, 1/6 of it, and then you plant the next year another 6, because sugar cane goes through a maturation curve where you get the max amount of sugar and then you go down, and then you take, and at the end, in the 6th year, you burn it all down and you replant it. And you just, so that's how it keeps going. And it's very good in Brazil, and they have no fossil fuel resources, and so for them it was necessity. It's more expensive, but it works. So the first thing you've got to remember is that 30% penalty you pay for, you know, I drove past the gas station, and you know, they had E85 at $3.85 and regular gas at $3.97, which you and I would say, well, I'll get $3.85 because until you do this. No, that ought to be about $2, you know, because you got less energy. So they didn't have the infrastructure that we had, and it was necessity, but they had all this stuff, and they were very well established. And we started this plant because it's easy to take ethanol, dehydrate it, make ethylene, make polyethylene out of it. And we were in the 4th year of planting and almost getting ready to start to build the fermentation thing. And the reason we did it is it was still cheaper to make polyethylene in North America with natural gas, but they wouldn't let you bring it in because of import duty. So if you wanted to serve that market, it's sort of like China and coal. Would we have done? No, but if that's the only, China said, you want to build a plant here, you got to use coal. I mean, so somewhere you got to work within the confines of the environment that you're in. And then they had this huge find of fossil fuels off Brazil's coast. And so today they've got this hodgepodge of, that plant never got built, because the truth is if you have ethylene, from ethane, which you always have associated gases or natural gas liquids, from a fossil fuel perspective, it was just way cheaper and better to build that out of their local produced gas. And I think the problem is that ethanol is still pretty expensive, and we still have a big debate about is the net CO2 emissions negative or not. And what I would say is sugar makes way more sense than corn. So, I mean, that's why I think they have another innate advantage. But it's interesting because I also was building this plant. I was down there at this big sugar refiner just to live in, and he had this ineffective, so you burn the biogas after you get the sugar out of it. They have all this biomass, you burn it, you make steam and use that to run your plant and do separations and actually generate electricity you can export. And it was a crappy old turbine. I was a GE, I knew enough about turbines, and I said, oh, you know, when we build ours, we're going to put more efficient turbines in here because that'll, you know, we'll get more output out. And he opens up this garage door, and there's like piles of gas out there. Bill, I don't need better efficiency. I have so much fuel to burn here. I don't need a better efficiency. So the economics, you know, are very interesting depending on where you are. And I think it's an innately advantaged opportunity because sugar is better than corn. You don't need the fertilizers. It's well established, and they have a lot of cars and infrastructure to move ethanol along. So I think
gas is basically free.
It's free, and it's at least carbon neutral because you know. They don't really use any fossil fuels other than the truck stuff, and so I think, but we're not Brazil, and so you can't extend Brazil to here, unfortunately. So.
We have questions from the Zoom participants, if there are no other questions. So maybe I'll read one of them. On the last slide, are we this dependent upon China because only China has the natural resources, or because we have just chosen to base production there because of labor costs?
Yeah, so this is a conscious choice of an energy policy. So China said, photovoltaics is strategic. I'm going to subsidize and help people and give them loans, and I'm going to be self-sufficient. So China tends to look at the world differently. So China, we as a global enterprise would look at the global balance. If there's an excess of supply, prices go down. China doesn't look at it that way. They say, if I'm importing 1 pound of something, I'm vulnerable and I don't want to be dependent. And so they consciously chose photovoltaic as to be a strategic opportunity. They said, I don't like the fact that you put tariffs on, and now I'm going to get you, and I can't import US-based ultra-pure polysilicon. And they subsidize the polysilicon market and all of these other parts of the value chain. There's not a single, and this technology was invented here and in Germany. We were the biggest people, and it's sort of like semiconductors. We let it go, and it's a, could we bring it back? Absolutely, but somebody's gonna, that's why, you know, it's just like the semiconductors. The government's gotta say, I want it back. We're gonna create appropriate incentives. We're gonna try to expedite the EHS, because the other things people don't understand is, to permit something in the US is awful. There is no resource issue here. The way you start here, the first step in the value chain, you take sand. That's all it is, SiO2. You heat it up with carbon, and yeah, you use 18 kilowatts per kilogram, but then you make silicon. And that silicon, then you turn into chlorosilanes, and then you ultra pure. It's amazing. The silicon in these plants is 7 to 10 nines pure. You know, 99.9999. There's nothing that we make that pure. There is no technology or resource barrier. This is a policy and a will issue. And but there's no advantage. China, actually, they have a disadvantage. The issue is if they're using carbon, coal-based electrical generation for all of this, it's not helping the world CO2. So, you want to take another one? Yes.
I understood that any alternative ways of producing energy right now are much more than fossil fuel. But I don't know what the projections for the damage from global warming are, but there certainly are some. Is it possible that that damage will increase to such a level that we will have to pay 3 times or 6 times or 4 times more for the energy because the damage from the other side will, like moving cities away from the coastal areas, and so on and so on. So is it possible that we end up, due to this third factor you didn't talk about, that much of this is going to be changed?
Again, I'll give you my views as good as all of yours. There is no doubt externality of CO2 emissions are not adequately captured in our current system. Right? I think that's not a contested question. The issue is, for what you would like to have that, then somewhere you've got to assign that back to somebody and put a cost against them, and that is a very tenuous connection. And so, do you charge the cement makers because you got to move Delaware inland a little bit? That's going to be politically, I just don't see how that's ever going to happen, right? I mean, you're going to end up with, to be able to say the things that I need to, first of all, you got to do it on a global scale. So you need China to participate, and then, a lot of these third world countries are saying, and the developed countries got to pay for us because we can't afford it. So, and I just struggle with, we just don't have enough resources to do all this unless you want to reduce defense spending, reduce infrastructure spending. Somewhere you're going to have to make that change. And we could do that. There's nothing magic, but I have never seen, I just don't see, especially when the energy policy changes every 4 years. Can you imagine, I'm going to run for president, and here's my proposal. Climate change, it's going to cost you guys not a whole lot, but your grandchildren are going to pay billions of dollars, and you're going to have way more hurricanes and tornadoes, and so I'm going to spend $1 trillion, and you're going to spend $1 trillion putting in solar, doing other things, and I'm going to cut out all the red tape so the EPA can't say I can't put photovoltaics there because of it's blocking the grass, or boy, I wouldn't have a prayer getting elected. And in the meantime, your oil and natural gas prices are going to go up. $5 is going to look cheap 5 years from now. I just don't, we don't like $5. And so it just seems we have and Europe really did screw up. We've got some good, they tried admirably to switch too fast. They shut down their solar, or their nuclear, and then they got dependent on, obviously not real people who like them policy. You need to have a self-sufficient policy, at least for the United States. We are very benefited in the fact that we have ample resources, but we got to get rid of coal, we got to get rid of fuel oil. I mean, we've got to be smarter with what we do. I think that you could sell, and you're just going to have to do it in a candid way. I just don't think saying you're going to pay more gets anybody elected. And or you try to, deficit spend that. You try to put another $2-3 trillion on us. Somewhere China's not going to. We're already at a very interesting. That's another. I won't believe it. We had the dollar on the gold standard. That went away. It became a dollar on oil standard. If Russia decouples from the U.S. dollar, our whole currency markets are going to be very disrupted. And so the ability for us to continue deficit stuff is dependent on other people willing to buy our debt. And if that's not dollar denominated anymore, it's pretty unstable. So I probably should quit, right? I bored you guys enough. I'm very appreciative of your time. And these are just some views. And I'd be first to admit I probably got some things wrong. But I didn't get the energy and mass or the cost or the scale. And when you see 1.5 cents a kilowatt hour, you guys say, wait a minute, explain where that's going to come from. And it's, because photovoltaic modules are down to $1 a watt. Hopefully you'll know enough now to say, yeah, that's not enough. Where are they going to come from? How are we going to make them? Are you going to be okay with being dependent on, China invades Taiwan and we can't get semiconductor chips anymore, but we can't get our photovoltaics for them? That just doesn't seem like a very good policy. I mean, it's a view. Again, I could be wrong. So I have been before. And Welch was a great CEO. I worked for him at GE. He just said, you're never going to be perfect, but you just got to get more right than you got wrong. Right? I think that's the thing with energy. We'll probably make some mistakes, but we can't spend $2 billion. We can't spend $128 million on sodium hydroxide for CO2. Right? That's the kind of nonsense we got to stop. So, if we could.
Thanks, Bill. Maybe one last announcement. Please keep an eye for notifications about our next seminar. Our speaker will be Daniel Nocera from Harvard University.